This video addresses a thermodynamic concept of flow work. To imagine it, consider this tube. There's a pipe with a large diameter up front, and it constricts to a smaller diameter, and fluid flows into this pipe, entering from the left. There's a high pressure that forces it through, and then it exits through the narrow tube. So there's some high pressure to the left and atmospheric pressure to the right. So it's accelerated as it flows into this narrow constriction. If I define a control volume, I'm just going to draw in red here. It's the inside of the walls of this apparatus. And believe it or not, there is work actually entering and leaving this control volume, and we call it flow work. The gist of flow work is that there's some energy required to push the fluid into this apparatus from the left, and there's some work required to push the fluid against atmospheric pressure, or effectively push atmospheric pressure out of the way. To conceptualize the flow work being done on the system at this upstream point, imagine a syringe. There's what's called a plunger, and if you push on the plunger, if there's fluid in here, it'll drive the fluid from left to right and out the nozzle. So if I draw the flow streams, we see flow flowing from left to right. To make that happen, though, there has to be some force acting on the plunger. And that force, if you were displacing or ejecting water from the syringe, you'd have to apply some force using your thumbs to push in on the plunger. And let's say we squeeze the plunger distance L from left to right. And I just applied a force over a distance, and I did some work on that system. And let's call that work flow work. So I'll say W flow, and that's equal to the force applied multiplied by the displacement, or the distance L. And on the left side of the plunger, there's some low pressure. On the right side, there's some high pressure that the plunger is pushing against to drive the fluid out. So we can say the net pressure, if I have atmospheric on the left and atmospheric at the exit, the net pressure is just this high pressure in here. And I can rewrite the force is simply the pressure times the cross-sectional area of this plunger and multiply that by L, and I've still got the flow work that I did. The volume of this cylinder is simply the area times the length. So I can say it's the pressure times the displaced volume is the flow work that was done. Let's look at the rate at which flow work was done, and we'll call it W flow dot, and that will equal the time derivative of the force times the length. And if we say that the pressure is constant, or consequently the force is constant, I can pull that out of the derivative, and I've got the force times the derivative of the length with respect to time. And again, writing that force is simply the pressure times the area, PA times dL dt, where dL dt now is the rate at which the plunger is being depressed from left to right. The area is a constant, so I can put that in the partial, and that's equal to P times dV dt. The rate at which flow work is being done is the pressure on the upside of the plunger multiplied by the volumetric flow rate of fluid flowing through this device. What's interesting, though, is a fluid doesn't know if it's being pushed by a plunger or if it's being pushed by its upstream neighboring molecules. An open flow process, we've got molecules pushing the fluid from left to right. And to characterize that, let's say instead of the plunger example, let's say we've got P times dmV, where m times the specific volume is simply the volume. And I'll move this up here to emphasize we're dealing with the open system now. So the pressure times the volumetric flow rate, the specific volume here is a constant, so I can pull that out of the differential. And I've got the pressure times the specific volume times dm dt. Or I could rewrite this, dm dt is m dot times p times the specific volume. And in an open flow system, you see this an awful lot, this mass flow rate times PV, and sometimes it's called PV work. So in the plunger example, we had to do work to drive the fluid through by pushing on the plunger. Let's not forget that the fluid also had to do work by pushing the atmosphere out of the way. To conceptualize this, let's look again. There's an upstream plunger pushing from left to right. So a force on the upstream plunger, and I'll call this F1. Now there's also a downstream plunger. It's representing atmospheric pressure in this case. If we assume that there's a vacuum or no pressure out here, then in this case the force acting from right to left is atmospheric pressure. And I'll call that F2 acting from right to left. Now I'll draw a control volume around this system, and the control volume contains the shaft of both plungers. And what will happen is that the upstream fluid does work on the fluid, and it depresses that plunger from left to right, and the downstream plunger is also moving from left to right, but it moves a greater distance. And it moves a greater distance because any displacement up here results in a larger displacement down here because the velocity of the fluid is greater as it flows through this constriction. So just like the open case, in this case, there's flow work being done on the system on the left, and the system is doing flow work on the right, in this case against a plunger, but in often cases it would be against the atmosphere if it was a free jet, or its downstream neighbors if there was fluid flowing downstream. And again, I can conceptualize these with the two pistons. Because the cross-sectional areas are the same, the pressures are the same, the pressure pushing from left to right on this piston will be the same as the pressure pushing from left to right on this piston, so positive work being done on the left, the system doing work on the right, and work being done on the system on the left. And as demonstrated here, flow work being done on the system on the left and the system doing flow work on the right. And for this example, the amount of flow work done on the system on the left just balances the amount of flow work the system did on the right. And as a final example, flow work occurs even in very simple geometries. Here I've got a pipe, diameter is constant throughout, and fluid flows from left to right. And if I drew a control volume, again I'm going to enclose the walls of the pipe and all the fluid inside of it. Believe it or not, flow work is being done on this control volume, and the fluid within the control volume is doing flow work on its downstream neighbors. And it may be no surprise, but the amount of flow work done on the system is equal to the amount of flow work that the system does. Again, I can conceptualize this with the two plungers. You'll see the force of the plunger entering the control volume on the left will equal the force of the plunger leaving the control volume on the right because the cross-sectional areas and the pressures are the same. So here it is. Flow work being done on the system on the left, the system doing flow work on the right.